Hello everyone, I hope you are doing well. In this video we are going to solve the problem 9 from chapter 7 of Introduction to Statistical Mechanics by Roger Bowley. Let's quickly see the problem statement and dive into the solution, okay, because we are running short of time. And here we go, the problem 9. Calculate the partition function of a relativistic particle in 2 dimensions. You will need to use polar coordinates to describe k-space. Before that we have done that thing, to find out the partition function for a relativistic particle in 1 dimension and in 3 dimensions as well. Okay, the solution to the problem has already been uploaded and you can practice it. In this problem we are told to do it for 2-dimensional case. This is super easy as well. You just need to know the formulas, okay, and once you are familiar with the problem statement and how you are gonna use the formulas, then it's not a big deal. You'll handle it, okay. The formulas remains the same because they are the general formulas. Even if it is a relativistic particle or something else, you have to use the similar formulas. The formulas wouldn't differ. Only the substitutions that you will make, for example, the value of energy that is given will vary for different systems, but the main formula remains the same. Okay, now let's dive into the solution. We need to find out the partition function for a relativistic particle in 2D. Okay, so let's remember the 2D formulas. Solution. We know that the partition function is given by, in terms of density of states, or it's up to you. Okay, z is equals to the limit from 0 to infinity. Okay, and then we have d of k dk e to the power minus e of k by k bt. Okay, here E of k means energy expression that has been expressed in terms of k. This is the formula that you'll use no matter if it is 1D case, 2D case or 3D case. You'll use this formula. Okay, the only difference comes when you will put the value of d of k. Nothing else will change. So for 2D case, for 2-dimensional case, d of k is given by a k by 2 pi. Okay, you just simply have to put this thing right here, but before that we should know what is the energy expression that we'll put here. And this is for a relativistic particle with momentum very much greater than its rest mass. We have the energy equals to Pc, and P is equals to h cut k. Okay, so we'll put since P is equals to h cut k, that is true in all the cases. So h cut k will put h cut k, c remains the same, h cut c is constant, so I'm writing them side by side, and k. This is the energy expression. Let us call it as equation number 3. We'll put 2 and 3 right into expression number 1, and let's see what we are going to get. Okay, a by 2 pi are constant, so I'm taking them outside. Okay, k e to the power minus h cut c by k bt, these are constants, into k dk. Now we need to solve that integral, and after solving it and simplifying it, we'll get the final result. And this integration is super easy. We use integration by parts method, in which k will be taken as first quantity and this one will be taken as second quantity. I hope you people know how to do integration by parts. The formula is super easy, and I'll speak as I write, so that you know as you people know, k is the first term. If I am saying first term, then it means I am talking about k, If I'm saying second term, it means I'm talking about this exponential term. dk is, part of integral, so it's not a part of second term. So first term as it is, k comes as it is, integration of second term h gets c by k b t into k dk. Okay, no limits of integration here. Limits of integration will appear upon the whole quantity, so you will not write it right here on these integrals. Okay, then derivating the first term, integral sign, then derivating the first term. First term is k with respect to k, because integration was with respect to k. We are giving so much respect to k. And after derivating it, then this term again, integration of second term again. Be mindful of kb and k, don't mix them. Kb is Boltzmann constant, it's a constant quantity, while k is the wave vector and it's not constant. After solving this integration and doing this differentiation, the result that we'll obtain will be integrated again with respect to k. Okay, and closing the brackets, and limit of integration will appear here from 0 to infinity. We'll solve all of these things, and after solving it, the result will experience the joy of limits of integration. So k as it is, this integration is, the term remains, the term comes as it is, divided by the derivative of power. Power is minus h gets c k by kb t. Okay, we have the integration of this term to be equals to this only if k has one power on it. If it would have been k squared, k cube, or k4 or something like that, you cannot use this formula. Okay, that wouldn't be correct. This formula holds only if the power is 1 on the variable in exponential. So the exponential term comes as it is, divided by the derivative of its power, minus dk by dk is 1, so it doesn't make effect, and integration of this term is similar to what we wrote before, and here we go. We have done this thing in previous problems as well, and k and 0 to infinity. A over 2 pi k e to the power minus h cut c k by k b t divided by this negative sign minus h cut c by k b t comes out of the integral, and it is only applied on k, and derivative of k is 1, so that is the final result, minus this thing again, k b t minus h cut c by k b t. This is the derivative in denominator. Okay, then it's a by 2 pi, this will come in numerator, k b t k minus h cut c e to the power minus h cut c k by k b t. This minus and minus multiplies and comes plus, k b t comes in numerator and comes out of the integral because they are constants, and again we have this exponential term right here. Sorry for the bad writing because I'm running short of time. I hope you are understanding what I'm writing. k b t minus h cut c e to the power minus h cut c k by k b t plus k b t by h cut c. Integration of this is again what we have done before. Okay, similar result will be obtained. We will get minus h cut c by k b t in the denominator, and limits of integration from 0 to infinity. A by 2 pi, we have minus k kbt by h squared c power minus h squared c k by kbt. This minus and minus becomes this minus and plus becomes minus. Kbt multiplies in numerator, kb square t square by h squared square c square e to the power minus h squared c k by kbt. Now it's time to apply the limit of integration. A by 2 pi, upper limit. Okay, when upper limit infinity is inserted, you will not insert, you will write minus kb t by h squared c are constant, so I'll write it as limit k approaches to infinity, k e to the power minus h squared c k by kbt here for this. Then this term kb square t square, since they are constant, so it doesn't make sense. K approaches to infinity, e to the power minus h squared c k by kbt. Then minus sign from the formula. This is the upper limit applied on this whole thing, minus into low limit on it. So low limit is 0, so we'll simply put it right here. If you put 0 in place of k here, 0 multiplies with the whole quantity and makes it 0. So it's 0 simply here. Minus in power, we have this thing, kb square t square by h squared square c square. In power we'll put e to the power 0, because 0 here we have k, and we'll put k is equal to 0 here, then it will multiply with the whole power to make it 0 as a whole, so it's e to the power 0 that's left. Okay, okay, so in next step, here you will not simply put infinity in place of k here, okay, because there is a property of exponential that will be used here. E to the power negative of something is a very small quantity. If we have e to the power minus 200 and you put it in calculator, you will get 0. Okay, though it's not infinity, 200 is not a very big number, but even though e to the power minus 200 is taken, the result is so small that we take it as 0. Okay, and you put 200 in place of k here, it's 200, and e to the power minus 200 gives you 0, so they will both multiply to give you a 0 result. Okay, so as k approaches to infinity, it means as k becomes very large, okay, through 100, through 200 and 500, this whole quantity becomes 0 very earlier, okay, then reaching to infinity, such that this whole quantity remains 0 afterwards. Okay, and we can take it as 0. The thing will not change, hence this whole thing, that whole limit will be equals to 0. Okay, this whole thing reaches to 0 well before k approaches to infinity, so we know, we can approximate what the answer would be. So you will put infinity in exponential term, so that if you put infinity in exponential term, you get this thing, e to the power minus infinity, and the power becomes positive when you write it like that, and e to the power infinity is infinity. Okay, and whenever infinity is 0, that is why we took 0 as the result. And similarly here, limit k approaches to infinity, if you put infinity in power, it becomes e to the power minus infinity, and the answer is 0 again for this. Then we have negative sign, 0 minus this e to the power 0 is 1, so it's 0 minus kb square t square by h square c square. Rest of all the values are 0, but this one is non-zero. this whole multiplies to give 0, minus 0, minus gets multiplied with the inner quantities, and minus is plus. kb square t square by a square c square, and these things just vanishes. a over 2 pi, we have kb square t square by h square c square, and this is the partition function for a relativistic particle in 2 dimension, such that its kinetic energy or momentum is very much greater than its rest mass, so rest mass energy. And yeah, that is it. This is the final result. I hope you people understood it, and share it as much as possible. That would be a great favor from you people for me, and wish you all the best. If you have any question, you can ask me in comment section, and I'll try my best to upload as many problems, as many helping stuff as possible. Okay, so good night for now because it's too late and I'm getting sleepy.